There is a slab of ice on the other side of the planet from you, and it is holding back enough water to put roughly 2 feet on every coastline on Earth H. Scientists at the British Antarctic Survey now say that slab is very likely to break apart this YAR, not in 50 years, this year. And if you live on the east coast of the United States, the water that shows up when it does will not arrive evenly. It will pile up on your shoreline harder than almost anywhere else on the planet. That's not a typo, and it's not exaggeration for views. It's gravity, and I'll explain exactly why in a few minutes. But first, you need to understand what this glacier actually is, because the nickname Doomsday has done as much damage to public understanding as it has done to generate clicks. Its name is Thwaites. It sits in West Antarctica, and its drainage basin covers about 192,000 square kilometers, roughly 74,000 square miles. That's bigger than Florida, close to the size of the entire United Kingdom. Where it meets the ocean, the ice front stretches about 120 kilometers across, making it the widest glacier on the planet. Not one of the widest, the widest. If you stood on one edge of that ice front, you would not be able to see the other end of it. And where the base of this glacier finally lifts off the seafloor and starts to float, the water underneath is somewhere between 800 and 1,200 meters deep. Hold on to that number because it's the single detail that separates Thwaites from every glacier you've ever seen photos of in Switzerland or Alaska. Here are the two numbers that earned this glacier its nickname. If Thwaites collapsed entirely on its own, global sea level would rise about 65 centimeters, roughly 2 feet, everywhere on Earth, permanently. Serious, but survivable. The number that actually worries scientists is the second one. Thwaites isn't just melting on its own. It functions as a plug for a much larger body of ice sitting behind it, the entire West Antarctic ice sheet. If that whole ice sheet went, global sea levels would rise about 3.3 meters, 11 feet. I want to be precise here, because this is the exact point where most videos with this glacier in the thumbnail stop being honest with you. Nobody credible is telling you 11 feet of sea level rise is coming up. During this century, full ice sheet collapse is a process understood to take centuries, possibly millennia. It's not a forecast, it's a ceiling. It tells you what's stacked behind the door, and Thwaites is the door. There are hundreds of glaciers in Antarctica. Thwaites gets singled out because of the shape of the ground underneath it, and it's genuinely strange to picture. Normal glaciers sit in a valley where the rock gets higher as you move inland, like a bow, tilted so the low point is at the coast. Ice slides downhill toward the sea because gravity pulls it that way, and the geometry works in your favor. Retreat inland means retreating onto higher, shallower ground, which naturally slows the retreat down. Thwaites does the opposite. The bed underneath it is below sea level, and it gets deeper the further inland you go. Geologists call this a retrograde slope. It turns the whole system into something closer to a bowl tipped the wrong way. Here's why that geometry is dangerous. The point where a glacier stops resting on solid rock and starts floating on seawater is called the grounding line. It's the hinge of the entire system. On a norm glacier, if that line retreats inland, it retreats into shallower water, and the retreat tends to choke itself off. On Thwaites, retreat inland means retreating into deeper water. Deeper water means a taller wall of ice exposed to the ocean. A taller wall means more melting. More melting pushes the grounding line further inland, into water that's deeper still. Every step makes the next step easier. Scientists call this marine ice sheet instability, and the plain language version is, once this process runs far enough, it stops needing outside pressure. It starts feeding itself, and there's something down there actively feeding it. The water in the Amundsen Sea isn't the icy surface layer you're picturing. Below that cold surface layer sits a deeper, relatively warm, salty current called circumpolar deep water, and tea has been finding its way along the seafloor and directly into the cavity underneath the glacier. Thwaites isn't primarily melting from warm air above. It's being eaten from underneath, in the dark, in a cavity no human being had ever seen, until a team of scientists decided to go look. In early 2023, 2 papers in the journal Nature described what happened when researchers drilled a borehole 600 meters straight down through the ice and lowered a torpedo-shaped robot called Icefin into the cavity below. It was the first direct look at the grounding line of Thwaites. What it found wasn't what the models predicted. Across the broad, flat underside of the glacier, melting was actually slower than expected. Somewhere around 6 to 18 feet per year, less than assumed. If the story stopped there, it would sound like good news, but the underside of this glacier isn't flat. It's a carved, irregular landscape of terraces and deep crevices cut up into the ice like staircases. On the steep walls of those features, melting was dramatically faster. The heat wasn't spreading evenly across a smooth ceiling. It was concentrating sideways, into the cracks. Over the 9 months the instruments recorded data, the water in that cavity stayed warmer and saltier than expected, holding well above freezing through most of the space, meaning there was always heat available to do damage. The takeaway researchers walked away with is the one worth remembering. The big pest threat to Thwaites isn't slow, even melting. It's fracture. The ocean is working its way into cracks and prying them wider. The glacier isn't dissolving like a sugar cube. It's being taken apart along its seams. This is where the title comes in. Out in front of Thwaites sits a floating extension called the Thwaites Eastern Ice Shelf. Picture it as a slab of ice that's already off the seafloor, wedged sideways against an underwater ridge. That ice shelf itself doesn't directly add to sea level. It's already floating, so it's already displacing its own weight. That's where a lot of explanations get sloppy. Let me say it plainly. The ice shelf is not the flood risk on its own. The ice shelf is the break, because it's jammed against that submerged ridge, what scientists call a pinning point. It pushes back against the land ice behind it and slows how fast that ice slides into the ocean. Take the break away, and the ice behind it accelerates. That's the entire concern in one sentence. In December 2021, glaciologist Aaron Pettit of Oregon State University presented findings at the American Geophysical Union meeting showing fractures spreading across this ice shelf faster than expected, warning it could shatter within as little as 5 years. That warning went everywhere, usually stripped of its caveats. And it's the origin of most of the panic headlines you've probably seen since. 5 years later, here's the honest accounting. The shelf didn't shatter in that window, but it didn't stabilize either. Between January 2020 and January 2026, the speed at which this ice shelf flows tripled, reaching just over 2,000 meters per year. Huge far. Fractures have opened around the pinning point and along the grounding line. On the western side, movement has roughly doubled in the last 8 months alone. And now Robert Larder, a marine geophysicist at the British Antarctic Survey, has said the shelf is very likely to break up in 2026, this year. So the 2021 warning wasn't wrong about direction. It was early on timing, by a few years, on a system where a few years is genuinely nothing. That's the pattern across this entire field. Scientists are usually right about what is happening. They're far less precise about when. Here's the comparison that gives this video its title, and it isn't a rhetorical trick. It's a real difference in kind. Hurricane Katrina generated a storm surge that overwhelmed New Orleans and killed more than 1,000 people. Hurricane Sandy pushed seawater into the New York subway system. In raw, destructive power, those events are far beyond anything a glacier will do to you in your lifetime. A hurricane can take a city apart in 8 hours. Sea level rise cannot do that. On speed and violence, the storm wins, and it's not close. But run the clock forward, and the comparison flips completely. A storm surge is a temporary borrowing of the coastline. The water rises, takes what it's going to take, and drains back out to sea. The claims get filed. The debris gets hauled out. The town gets rebuilt on the same lots. Life resumes on the same map. Sea level rise doesn't give the land back. There's no draining phase. When the ocean rises 2 inches, it's 2 inches higher at every high tide, every storm, every full moon, for the rest of human history as far as anyone planning a city needs to care. It doesn't destroy a neighborhood. It reclassifies it permanently. And here's the part that does the real compounding damage. Sea level rise doesn't act alone. It acts as a floor under every storm that comes after it. Raise the baseline by a foot, and every hurricane that arrives afterward starts its surge a foot higher, over seawalls and drainage system. EMs that were designed and financed against the old number. It's the same storm, unchanged in strength, reaching further inland than it ever would have before. Sea level rise doesn't replace hurricanes as a threat. It upgrades every single one of them, permanently, without ever once showing up on a radar screen. This is the part of the title that sounds impossible until you understand the mechanism, so stay with me. You'd reasonably assume ice melting in Antarctica raises sea level evenly across the globe, or that it raises it most near Antarctica. Both assumptions are wrong. The reason is gravity. An ice sheet is an enormous concentration of mass, and mass exerts gravitational pull. The Antarctic ice sheet is physically pulling the surrounding ocean toward itself, holding a bulge of water close to the continent. When that ice sheet loses mass, it loses some of that pull, and the water, it was on the planet. Scientists call this a sea level fingerprint, and it produces a result that sounds backward the first time you hear it. When Antarctic ice melts, sea level near Antarctica actually falls. The rise shows up thousands of miles away instead. The American coastline sits on one of the places where it shows up hardest. According to NASA, when the Amundsen Sea sector of the West Antarctic ice sheet, the sector Thwaites belongs to, is entirely gone, average global sea level rises about 4 feet. But the east coast of the United States sees an additional 14 to 15 inches on top of that global average. Run the numbers. The world gets 4 feet, and the American East Coast gets more than 5. The United States isn't a bystander to Antarctic ice loss. It's one of the places on Earth that gets hit worse than the global headline number implies. And the mechanism isn't weather or currents or bad luck. It's the gravitational field of a continent of ice on the far side of the planet loosening its grip. None of this is a future problem you get to file away, because the American coastline is already shifting without any help from a Thwaites collapse. NOAA's Federal Sea Level Rise Technical Report projects the U.S. coastline will see an additional 10 to 12 inches of sea level rise by 2050. That means this country is on track to see as much sea level rise in the next 30 years as it saw in the previous 100. A foot sounds like nothing. You could step over a foot of water. The problem is that coastlines don't experience averages. They experience their worst day of the month over and over. Under current projections, flooding along the American coast is expected to happen more than 10 times as often as it does today. By 2050, high tide flooding is projected to occur somewhere between 45 and 85 days a year, depending on location. Charleston, South Carolina, sits in a range closer to 45 to 115 days. The Norfolk, Virginia area is projected to see something closer to 100 days a year, 100 days out of your year. That's not a disaster. Nobody deploys the National Guard for high tide. It's water in the street on more than a quarter of the days in the year, with no storm involved, in cities that were never designed for it. It's the kind of flooding that doesn't kill people, but quietly kills property values, insurance markets, road surfaces, septic systems, and the tax base that has to pay for fixing any of it. And that projection is the baseline. It's what happens with the ice loss already in motion. Thwaites is what could stack on top of it. Here's the direct question, answered with the science instead of the thrill of it. Is Thwaites about to collapse? Is Miami about to go underwater in the next decade? The honest scientific answer is no, and you deserve to hear that plainly. Most videos with this glacier in the thumbnail debut won't tell you that part. There's no evidence Thwaites has entered a runaway collapse. A full collapse isn't expected within the coming decades. The most likely path is a glacier that keeps retreating faster through this century and into the next, with the truly enormous outcomes measured in centuries, not years. And in one specific way, the science has actually moved in a reassuring direction. The kind of update that never makes a headline. There was a hypothesis called marine ice cliff instability. Once floating ice shelves are gone, you're left with towering ice cliffs at the coast, so tall they and support their own weight. They'd crumble, exposing a new cliff behind them, which crumbles in turn, and the collapse runs inland like falling dominoes. That hypothesis generated the most terrifying sea level projections of the last decade. In 2024, a study published in Science Advances, led by Mathieu Morligam of Dartmouth College, tested that hypothesis using 3 separate high-resolution ice sheet models. The finding, ice cliffs need to reach roughly 100 to 135 meters, about 440 feet, before that kind of systemic failure even begins, and they fail far more gradually than the original hypothesis assumed. When the team simulated a total collapse of the floating ice shelves today, all 3 models showed the ice sheet remaining fairly stable through at least the year 2100. The domino scenario for this century doesn't hold up. That's a real correction, and it deserves to be said out loud. But listen to what happens next, because this is where the honesty cuts the other way. Marine ice cliff instability, in the study author's own words, is only one mechanism of ice loss, and the finding does not mean Thwaites is stable. What that study removed was the fastest possible route to catastrophe. It did not remove the destination. The ocean underneath is still warm. The bed still slopes the wrong way. The fractures are still spreading. The grounding line is still retreating. Along the Amundsen Sea coast, it is already withdrawn by as much as 42 kilometers in places. Thwaites is losing ice more than 5 times faster than it was in the 1990s, and it has shed more than 1,000 billion tons of ice since the year 2000. One modeling study, published in March 20th, 26 projects that by 2067, this single glacier could be losing between 180 and 200 gigatons of ice a year, roughly comparable to what the entire Antarctic ice sheet is losing today. The accurate summary isn't that the danger got canceled. It's that the mechanism changed and the clock got longer. The direction never changed at all, and a slower catastrophe isn't a smaller one. It's one that arrives on a schedule no election cycle, no 30-year mortgage, and no municipal bond was ever built to think about. It's worth zooming out for a moment because Thwaites doesn't sit in isolation. Right next to it is Pine Island Glacier, its neighbor in the Amundsen Sea sector, and it's been retreating on a nearly identical timeline for the same underlying reason. The same retrograde bed, the same warm water finding its way underneath to get it. Thwaites, and Pine Island are sometimes called the weak underbelly of West Antarctica, because if either one goes, it changes the stress on the ice sitting behind both of them. Researchers monitor them as a pair, not as separate stories, because a change in one tends to show up in the other within a few years. That matters for a simple reason. It means the one glacier framing in most headlines actually understates the picture. Thwaites is the fastest moving, most studied, and most consequential piece of this system, which is exactly why it gets the spotlight and the nickname. But it's the lead-in G-edge of a broader retreat happening across an entire sector of the continent, not an isolated freak event. When scientists talk about West Antarctica as unstable, they're describing a regional pattern that Thwaites happens to illustrate most clearly, because it's the one we've managed to put instruments on. It helps to know what the ocean has done before, because it puts the current numbers in perspective. Global average sea level rose about 8 to 9 inches over the entire 20th century, a slow, mostly unnoticed drift that coastal engineers had 100 years to design around. NOAA's sea current projections have the U.S. matching that entire century's worth of rise in the next 3 decades alone. That's not a subtle acceleration. That's the same amount of change compressed into roughly a third of the time, hitting infrastructure, drainage systems, and building codes that were never built for that pace. Go back further, and the perspective gets stranger. During the last interglacial period, roughly 125,000 years ago, global temperatures were only modestly warmer than today, and sea levels are estimated to have been somewhere between 20 and 30 feet higher than they are now. Much of that extra water is believed to have come from a partially collapsed West Antarctic ice sheet. The same ice sheet Thwaites is currently holding a door shut on. Nobody is suggesting that Thai is an imminent scenario, but it tells you the ice sheet has done this kind of thing before under conditions not wildly different from today's, and that the geological record takes the retrograde slope physics seriously even without a human being around to measure it in real time. There's a version of this story that never gets attention because it doesn't have a dramatic visual, the actuarial one. Coastal property in flood-exposed zones is already being quietly repriced by insurers who don't care about headlines, only about payout probability over a 30-year mortgage. Florida's state-backed insurer of last resort has grown in for years as private insurers pulled out of high-risk coastal counties. Some coastal towns have seen property tax assessments and insurance premiums diverge sharply from home prices, a pattern researchers call the insurance gap, the point where a house is still sellable on paper but functionally uninsurable at a price NEO, NE can afford. That gap tends to widen years before the flooding itself becomes visible on a street, which means the financial consequences of sea level rise typically arrive at a property before the water physically does. If you're thinking about this purely as a future physical risk, you're already behind the market that prices it. The thing to watch over the coming months is the eastern ice shelf and its pinning point. If it breaks up this year, as Larder and the British Antarctic Survey expect, scientists will immediately start watching how much the glacier behind it speeds up and how fast. That measured number, not a modeled one, will do more to sharpen sea level projections for the American coast than any argument online ever will. Now here's what you can actually control, because information without an action attached to it is just a heavier kind of worry. Go find your actual elevation and your actual flood zone. Not your neighborhood's, yours. FEMA publishes flood maps, and NOAA publishes coastal flooding viewers that show exactly what a given amount of water does to your specific address. Most people who live near water have never once looked, and the ones who assume they're fine are frequently wrong by a margin that matters. Understand that a standard homeowner's policy does not cover flood damage. It never has. Flood coverage is a separate purchase, and there's typically a 30-day waiting period before a new policy takes effect, which means the week a storm shows up in the forecast is already the week it's too late. That's a conversation to have in a calm month, not a hurricane week. If you're buying property near the coast, ask for the elevation certificate and ask about the property's actual flood history, not just its flood zone. Zones get redrawn on paper. Water doesn't consult the paperwork. And if you're renting or the property decisions aren't yours to make, focus on the go bag and the plan. Documents, medications, water, a way to charge your phone, and one meeting point every person in your household knows without being reminded. We've built our entire relationship with the ocean around events. Hurricane seasons, evacuation orders, landfall, and then the counting starts the moment the storm passes. Every institution we've built F or coastal risk assumes the water comes, and then the water goes. Insurance is priced that way. Building codes are written that way. Mortgages are underwritten that way. Cities are planned that way. Thwaites doesn't care about any of that because it isn't an event. There's no landfall and there's no all clear. There's no moment when the water goes back out and the counting resets because the counting never stops. That's the entire difference this title is pointing at. A hurricane is an ocean that's visiting. This is the ocean moving in. The first is a catastrophe you survive and rebuild from. The second isn't a catastrophe in any way we currently know how to recognize. And that's exactly why it will beat us if we let it. It's slow enough to ignore, permanent enough that ignoring it compounds, and driven by a piece of ice so far away that no American will ever see it with their own eyes. Go find out what your address sits at above sea level. Do it this week, not the week you actually need to know.